Hello. Well, hello everyone. Thank you for attending the third day of the QTYR workshop Congress. And today we have the pleasure of listening to the talk of Juani Bermejo Vega. Juani did a bachelor's degree in physics and computer science in the University of Salamanca, and then moved on to do a PhD at the Max Planck Institute for Quantum Optics under the supervision of Martin van der Nest on the group of Ignacio Cirac. There, she represented several PhDs and was part of a large PhD network where she founded an equal opportunity group. Afterwards, well, during the PhD, she went to do a stay at MIT, and afterwards she went to do a postdoc at the Free University of Berlin on the group of Jens Eisert. Then she received a Marie Curie Sklodowska fellowship and went back to Granada. And now she's a PI there with a group on quantum computing and machine learning with a Ramon y Cajal fellowship. So without further ado, let's thank her and listen to her talk.
Thank you very much. Testing the microphone. Are we doing karaoke tonight? Say yes, karaoke tonight, raise the hands. No. Uncertain. Yes to karaoke again. Who knows how to organize a karaoke tonight? Who knows someone who knows how to organize a karaoke? You tell me whom. Okay. Thank you for coming. We're going to start today's session. I'm going to be talking about quantum computing and classical simulation theory, related things, mostly about different things in quantum computing theory. I did my PhD in this topic, classical simulations of quantum computations. Is this laser working? Is it like this? I'm not sure this is a laser pointer. Careful, it's a laser. I have a laser pointer otherwise. Oh, okay, it's working. Otherwise, I have this one. To be honest, can I test this other one? Okay, I prefer to use mine. Okay, right. I was doing my PhD on classical simulation of quantum computing. It's a very weird topic, or at least it was at the time. People didn't get why would you want to do that. I chose to go back to my weird old topic because I want to start explaining quantum computation from there. Then, okay, I'm gonna introduce myself. I am principal investigator in Granada. Granada is in southern Spain, Andalusia. We have a group, we're called the Quantum Thermodynamics and Computing Group. We have the logo. We had a fight about the logo and the name of the group. We have 3 quantum PIs. That's me, Daniel Manzano, Michalis Skotiniotis. We work on quantum computing, quantum information, and machine learning. Also metrology in the case of Skotiniotis. a bit of quantum foundations. We also have Carlos Cano, who is in the computer science department. He's a machine learning person. He's also a senior. Several postdocs, Ria, Alexander, Julio Camilo, and Filipa Perez. Some of them have posters here. And in fact, there's one poster with Daniel and Ria. This is Alvaro, our PhD, Dolores, Lola, our PhDs. Noelia and Antonio Jesus are starting PhDs with me. They are just finishing their masters. And this is Rocío, who is our humanities postdoc and project manager. We are part of the Carlos Primero Institute, which is a facility research institute for computational and theoretical physics, and groups that are at the intersection. We have a small cluster in this institute, and I actually am working on building the cluster. Usually I've done more theory and algorithms, but recently I've becoming more interested in also high performance computing and machines. It's partially because the cluster is right in front of my office and I have to see it every day that I go into my office. At this point, I've been working in quantum computing since 2010. I've been publishing papers, and I think every publishing paper I publish more or less said that quantum computers don't work very well. Then I moved to Granada and they put this thing in front of me and it's like, come on. Yep, so this works very well. It's a dedicated cluster. It's not publicly accessible, it's not part of a network yet, but you can publicly request access. Basically, you just become a member of the institute if you want to use it. I'm building supernodes in here. So I'm gonna talk about my favorite topics in quantum computing. This is a bit of my trajectory. I am from Extremadura, which is the region in here. Extremadura is a part of Spain that importantly exists. Like many people haven't seen it, but it's there, okay? It's in the west of Spain. Spain has a west part. Like it's not the south, it's not the north, it's the west, okay? So we do have a west, and I'm from literally the west. This is the region of my parents. I was born in Cáceres and raised there until I was 18. Then I moved to university to Salamanca. This is actually part of Castilla y León, which is this area where they speak the purest form of Spanish, and they also don't know how to use pronouns. So, but the Spanish is very good, you know. Like it's just that their grammar isn't. Like, you know, this thing about inclusive language, and you know that in Spain we have now some proposals to have gender-neutral language, and people sometimes get pissed about pronouns like ella, and it's like some of these pure, like traditional conservatives who don't like to use gender-inclusive pronouns and from these regions, which is like Castilla, Madrid. In this entire area, they don't know how to use the pronouns la, le, lo. Okay, so I don't think they are serious when they are saying that they cannot. Yeah, you know, it's like I just don't believe that they don't care about they are against gender-neutral pronouns. I did my degree here. I studied. Actually, I'm not a bachelor in physics. Thank you for saying that. That means I look younger than I am. I am a licenciada in physics and an inferior engineer in computer science. Like there is this thing called a technical engineer in computer science here. Like, and then there is the superior engineer. So I guess I am the inferior one. And did these 2 degrees. Then I moved to do a PhD in quantum computing, and I did my postdoc also in quantum computing. He actually introduced that. Then I moved to Granada here. Then I came here to build a group, and then COVID appeared. COVID happened. There was massive cataclysms. We all got separated. I couldn't see many of you for a long time. Then a lot of people left the field. Then some people joined the field. Years later, we have conferences again, and it's a bit weird because it feels like 5 years have happened. It was very complicated to get funding and to basically do anything like shopping. And during that period, I got a baby. But after some years, I got funding. And I'm building a group. Now I have 3 postdocs and 2 PhDs. My funding mainly comes right now from Focaccia, a European project, a European-Canadian Horizon project. The Consolidación grant, it's kind of like a Consolidación, it's like similar to ERC, but it's smaller. And I'm a Ramón y Cajal researcher. These are my social networks. I am in many social networks. I'm queen of Quanta in all of my social networks. Basically, since X collapsed, I have profiles in most of them except TikTok. I'm also not using most of them, so I don't know why I have them, but sometimes I put things. Like, I'll recommend to use LinkedIn, to be honest, mostly because many of you here are in juniors. You don't know where you're going to go, research or academia or companies, but LinkedIn profiles are used a lot in quantum computing for hiring, also in tech and in computer science and in companies. So if one piece of advice I would like to give you is make a LinkedIn, because actually last week my postdoc had an interview in a company and he didn't have a LinkedIn and I had to call him out. Like, he's like, because it's like, what are you doing, man? So these are the topics I've done during my research time grouped. I started my PhD working on classical simulation methods for quantum circuits or quantum systems, like efficient classical simulations. You know, quantum computers are hard to simulate, so I was studying how to simulate them efficiently or to what extent you can do that. Also in connections with quantum algorithms, like to understand better how to design quantum algorithms by finding better ways to destroy them. And what something that is not efficiently, something is simulable efficiently, classically, that's not a quantum algorithm that is good. So it's a mechanism. Classical simulations in theory of computation are studied to understand what are the fundamental structures that power quantum computation, how to make better quantum algorithms, how not to design bad ones, also what are the quantum resources, the physical quantum resources that power quantum computation. And here we go back to foundations. In this area, I've been working on Wigner negativity in quantum computation or contextuality in quantum computation. Maybe you are more familiar with entanglement, like entanglement is a resource for quantum computation. Well, that's the kind of problems that people study in this area of foundational quantum computing and quantum resources. I do a bit of machine learning. I do classical and quantum machine learning. Actually, I prefer classical machine learning, mostly because I have a good cluster with accelerators and it works. And quantum machine learning, I'm so sorry, but as a person who investigates and research in quantum machine learning, I apologize for our field of quantum machine learning. Nothing works yet, so but we keep doing that. Been working on many-body theory. Adjacently, I've developed some works on tensor networks. Like this is a work on, this is not the majority of my work, but I have some, I think that one of the themes in more than many-body theory here is I like to study mathematical structures that power quantum advantages and quantum algorithms. And here we had a paper using tensor networks to classify computational phases of matter for measurement-based quantum computing, like using tensors to find phases that have power for measurement-based quantum computation. Also worked during my postdoc on near-term quantum devices. I don't know if somebody's working in companies here. I don't do this anymore in the university. Unless it's like a very foundational project. Because I used to work closer to experimentalist, but it's a lot of work, and I would prefer to be hired by a company and get paid consulting money for doing that if somebody's interested. But otherwise, I'm moving a bit more towards classical HPC and foundations. Anyway, I will tell you a bit about that. Some recent papers of the group, for instance, like this PRL came recently. It's a PRL on a simulation of quantum states using quantum error correction. Like it's an efficient classical method, and it's for simulating certain quantum error correcting code words with noise. The main author here is Cameron, and I would like to highlight that because he put a lot of work here and he's just finishing his PhD and he got a PRL, and I'm very happy like that he got it. We are doing quantum machine learning. I have to admit that Danny is the leading guy in machine learning. He's the person who pushed machine learning in the group. So Danny has a lot of interest in developing machine learning methods for classifying entanglement or detecting entanglement. He is also an entanglement theorist and studies quantum transport. So we have this paper where we use neural networks to basically detect whether their states are entangled, and we have another upcoming paper which is not yet in the archive, but is finished on using support vector machines to detect entanglement. Okay, more like classically here, or quantum SVMs use as a classical method. The thing is that in this research we haven't still found very reasonable advantages of quantum SVMs. There's another poster out there by one of you that is on similar topics. If you go to the poster session today and it's still there, I recommend you to look into it. A person who's here is Ana Marsabi, as a former student of mine, is now in Madrid in a company. Is still interested in these things, but she couldn't come to QTYR. So if you're interested in this, please let me know and I will introduce you to Ana. I would like to now have a historical moment. Like, I want to tell you, I see, the way, my background where I come from computer science and physics. Sometimes it's complicated to explain to people why I think these two things come together. The fun thing is, when you study two majors together, they are not different majors, they are one major. But anyway, I would like to go back to this industrial revolution and see that actually computers and physical machines are kind of the same thing. Do you remember that in the industrial revolution, it was on this moment when we started to automatize processes. We developed vapor steam engines using thermodynamics, and also at the same time we started to develop automatic computers. The first automatic computers were very similar to mechanical engines. This is a big, and also they were very physical. This is a picture of a memory, old memory. This is already an electrical memory, an electrical computer. The memories we had at the beginning, they were hand-woven. And the industry of the memories was basically at the beginning filled by women that came from the textile industry. Many of these were women of color. Now, the textile industry appears with the Industrial Revolution, it scales up. In the Industrial Revolution, there are important advances in science and technology that come up with things like the steam engine that, gives us trains, gives us new means of transport, and boosts international commerce. Also colonialism and extractivism. And this is responsible for a lot of the technology growth later in the 20th century and the 21st century. But also, at the same time, we have the engines, we have things like the loom. The loom is this machine that automatizes the creation of textiles. It's a sewing machine, un telar. Looms, at this time, developed computer cards. These were programs where you would actually put a program. The program is a set of instructions that tells the loom what they have to to sew. So it actually tells the pattern that they have to sew. This is an example of a computer as well. It's an early computer, mechanical computer. And I like to have this picture in mind because at this point, there is no real distinction between computers and physics. The thing is that later, a distinction appears. And I don't know what is your theory about why that happens, but I have one theory, and maybe we can discuss later what is yours. But my theory is those machines were mechanical, and those machines were made of different materials later on. In particular, electromechanical computers require electrical engineers, and these type of machines require other type of engineers. So because of the materials were different, 2 degrees were made. And it's the same degree. And also, we all come from philosophers. If there's a philosopher in the room, you're all guilty. Now, going back to now, we are in an era where physics and computers are becoming very close together again, because we have fields like quantum computing where we study how to make better computers using quantum phenomena. Now, if you study software development or computer science, you typically make this distinction between hardware and software. But it's not a real distinction. It's an abstraction we use to design complex systems. It is as if, we are people, we are humans, we are also a group. These are abstractions. But all the difference between hardware and software is not black and white. Quantum computers, for instance, are becoming more like a technology where you have to understand physics and computation at the same time. But also, I don't know how is any of you has a cluster in the lab or in the institute? Is your cluster giving problems near summer? Are they getting like shut down all the time because they have thermal problems and stability of the air conditioning? No? Well, in our faculty, the cluster has been like out of service several times because they get warm, and every year they get warmer. They get warmer, and I really know, people in Andalusia were super hot, but I think it's peculiarly hot in there. And the thing is that the last generation of supercomputing devices require more and more cooling because they use more and more power. The last generation of GPUs use a lot of power and they get really warm in there, and the air conditioning system is the demand of electricity is increasing. And we, right now, for instance, have to move our cluster to a dedicated room, or it will eventually stop working. So the classical computers are kind of becoming like quantum ones from the other side. Like they are becoming more unstable, they require cooling. And now here's the thing. I want to ask you, are quantum and classical computers different or the same thing? Who wants to give an opinion? I'll give you 5 minutes to think about it. Okay, this is a classical picture of coherence. But here I'm showing the fundamental phenomenon that powers quantum computers is not very clear, but one of them is coherence. Coherence is, having microscopic phenomena at scales where we can observe them and control them. Like we all know that when we go to the microscopic world, there is physical phenomena that is there, but sometimes we don't see because there is noise. Like for instance, atoms can be moving in all directions. I think for me, this is like doing a karaoke in a workshop, like this one, or being in a bar. At some point in the night, there is noise, and people are drinking Fanta and Coca-Cola, and somehow they become more noisy, and the sense that they become more like a liquid. They have a phase transition from a solid state where they are like sitting close to each other and having a very calm conversation, and they talk about politics or football or algebraic structures in quantum algorithms. But then after 6 or 26 songs in the karaoke, they are more like that. Okay? So because there's a background noise in the karaoke. Yeah? There is like drinks, and also more people enter, and there is less space, and you get overstimulated, and it gets hot. Now, when we cool down a system or a karaoke, things become more rich in phenomena. Like people conversations become more varied, and also atoms, like cold atoms in an optical lattice, we can observe more quantum phenomena in there, like entanglement, interference, or the tunnel effect. And we know that this has applications in computation as well as other technologies. Like this is standard. We know that there is a quantum algorithm that can be run in a quantum computer that solves the factoring problem in polynomial time. And the best classical algorithm that does that has exponentially scaling resources. So there is a problem that we've known since 1994 that we don't know how to solve with classical computers efficiently, and we do for quantum computers. And this problem was important because it's a very important problem in cryptography. So the discovery of this changed the world because it means we have to change our cryptographic systems to make them secure. However, although there is a polynomial in here, when you make resource scalings for what type of, sorry, I'm confused. I'm going to the wrong direction. If this is a picture of how big of a classical computer you would need to solve the factoring problem to a reasonable size to break crypto systems right now, at least with publicly available data. Maybe the Mossad has a better system to do it, but you never know. Then this is like an estimation of how big of a cluster you will need to break RSA. These are cryptographic systems that are everywhere. In particular, wherever you go to a web page in a browser, in Chrome, Firefox, whatever, and you see a little lock in there, you open, it says there is a secure communication with the web server. Usually the protocol is RSA, and RSA uses the difficulty of the factoring problem to work. It's, however, very hard to solve the factoring problem in a quantum computer. There are estimates, people who work into this, you want to know how realistically can we build factoring in a current computer. So the people, you can actually do that. People who do these kinds of investigations have a background with a mixture of quantum error correction, quantum synthesis, quantum compiling. It's complicated, but you can make reasonable assumptions on what hardware you have and what the quality of your chip is and get numbers. This is not the most recent study, but typically the resources for implementing the factoring algorithm in a scale of practical relevance are way out of reach of current technology. Like typically we need millions of qubits in lots of different studies. This is a roadmap of what is going on with quantum technologies in general in Europe. It's an old, this picture was made years ago when the quantum flagship appeared. So this is how the European quantum flagship was envisioned. In Europe, the strategy was to invest in different areas of quantum technologies divided as atomic clocks, sensors, quantum communication technologies like internet, quantum links, and quantum simulator technologies and universal quantum computers as computational devices. Do you know the difference between a quantum simulator and a universal quantum computer? Sometimes people say, like, are quantum simulators just experiments? And in a way they are, actually, but also they are models of computers. Like, these are, you have a system in your lab with unconfigurable parameters. You configure the parameters to imitate another program or system. The main difference here is that the system is not universal. You cannot run an arbitrary program in there, and you have to configure the device to work at the beginning. So it's actually a kind of computer. In fact, we'll see later, it's like a field programmable gate array in principle, another type of classical computer. But it's in a quantum simulator, you basically specialize the quantum computer to a single job, typically the simulation of some aspects of a quantum system. And a universal quantum computer is more ambitious. It's a machine that should be able to run any program, any quantum program, simulate any unitary efficiently, or you should be able to approximate sequences of local circuits, approximate any unitary. When we study quantum technologies, it's important to consider the ethical backgrounds, the ethical frameworks where we should build quantum technologies. Now, quantum technologies are being built for real. They're no longer hypothetical devices. As in other areas of computer science or artificial intelligence, it's important that we become more conscious about their real-life effects. As you see now, for instance, the appearance of last generation LLMs in artificial intelligence has changed the world entirely. So this is the kind of thing I'm talking about. Like, when we make these technologies, we should talk about what are the possible ethical implications, mostly to design in advance good and appropriate uses of them. Like, and some of the ethical problems we should consider here, well, like quantum computers have obvious military applications, like most things in physics. I'm not saying we are special. Physicists are great at having military applications. Like, I'm a physicist. I might declare myself guilty. But anyway, they have for cryptography, for sensing, for radar, like sensing, quantum sensors. Radar can use, for instance, quantum entanglement and a phenomenon known as quantum illumination to improve radar sensitivity. It's a hypothetical device, but it's being investigated, for instance, in Canada. We can break crypto attacks. If somebody right now has a quantum computer and doesn't say so, they're breaking your cryptography probably. Also, people with access to decent quantum simulations will have an advantage for materials research. As quantum computers can basically run artificial intelligences and algorithms that extend our current algorithms, we have the same ethical problems as AI in general, and maybe a few more. But you know, AI are problems that of ethics in AI. As like when you train an AI, are you training them to do something good or bad? Are you automatizing a process, or are you training them to do evil automatically? Some AIs, for instance, can discriminate and be racist. And AIs trained by the police in Spain can declare guilty Romani people more often. Or some AI is trained on, I don't know, databases, can label people of color wearing suits as the N-word, whereas they will label white people wearing the same suits as lawyers. Those are things that are important problems. Then there is a problem of resources. These things are expensive. How do we build them? How do we build them ethically, and how do we do it sustainable? Where do the resources come? How are they extracted? Which countries have mines of the resources? And how do we extract them? There is a problem here with extractivism, right? So there is a problem if the computers end up being restricted. The technology is owned by northern countries and the resources are coming from the global south. Well, there is a problem in there. This is a picture, for instance, what I was mentioning, the quantum radar. These are the papers that the quantum radar is based on. At this moment, quantum radar is more a fantasy of a reality, but for instance, the government of Canada has been funding research projects to develop it. And there is this thing here, like when you're working in the arms industry, there are different types of people. Some people are like, you're working with your army from your national country for defense. Good, okay, that's one type. It's actually, in my opinion, that's the best, most ethical type. Because here come the others. Like there's people who will develop technologies for profit, but they are absurd technologies and they have absolute no application, but it's a speculation over war. And then in between, there's things like this. This is like, basically the motivation why Canada is funding the research is geopolitical. They want to assert, gain Arctic sovereignty, and there is parts of the Arctic that Canada declares to be part of Canada. Other countries disagree. Very often the United States, but not always. Not only the United States. Also there is parts with Russia and other countries and Europe. And Canada, for instance, has programs to improve submarines, to delineate very well what is the frontier of Canada. And they also invested in this type of programs to show that they have activity over the Arctic. They have also moved populations of Inuits from here to up north to claim that people live in there, which is a pretty extreme thing to do. Anyway, so these are typical ethical issues. If you want to have a discussion later, I'm happy to continue. I want to continue with the topic of the research. So, okay, I'm going to start with talking about classical simulations. Okay, before going to quantum algorithms, I'm going to talk about why would we want to understand when a quantum computer is classically simulable. One of the reasons is, as I said, to understand what resources are important in quantum computing. Several identifying classes of computations that are classically simulable. We, as a community, we have learned, for instance, that in quantum advantage is partially powered by resources like entanglement, contextuality, or interference. None of these resources is the explanation of why quantum computers work. We just know these are necessary features of quantum computers in order not to become efficiently simulable. So you have little entanglement of certain types, you are simulable with a tensor network. The largeness of the Hilbert space is like another feature, although it's not quite right a resource. And the area of when you study fault tolerant circuits, like Clifford circuits appear, which is a family of circuits I'll explain later. And there we have gained insights into contextuality as a resource for quantum computing. Now that's a fundamental motivation. There's also practical motivation. Like quantum computers, as they exist now, I like to say they advance in quantum superposition because it seems that they are super amazing and super bad at the same time. Like honestly, why do I work in quantum computing? It's because I find them fascinating. I love them. They are like the coolest thing ever. I also have to admit they don't work very well. It's a bit like when you have a tiny kid. I have a 4-year-old, and it's the most amazing thing on the planet. But they cannot do large calculations. But they can climb better than me. Anyway, we have right now devices with many qubits, 50 to 1,000 qubits. It depends on what type of control, what type of hardware. The number of qubits is not a single metric. You have to look more into things like the volume, the control, the noise. But anyway, more or less, these are typical numbers depending on what architecture you have. They are not so big, but they are not so small. These are cool computers. These are very amazing computers, like history book computers. There is public initiatives and private companies now trying to develop quantum computers. We have publicly accessible quantum computers in many countries. In Spain, right now, we have 2, in VSC and in CESGA. DIPC is buying another one, and we are also having similar initiatives in other countries, in Italy, in most of the European Union ones, I think. In the theory side, or in the application side, we also have a problem, like we know applications, but they are hard to implement. And if we want to do applications with what is available, they're hard to find. So we have a situation where we haven't yet found a killer application of the devices that we have right now. Yeah, I think so. We can discuss. I think if we have found one, probably the person who found it didn't say anything. Okay. Okay, so one of the reasons why I care about classical computers, classical computation simulation, is a theoretical one. Like in theory of computation, I like to understand very well when do I need to use a quantum computer, when a classical one. And in the context of algorithms, when I want to develop a quantum algorithm, or even a classical one, I want them to have sometimes interesting features. One of them, for quantum algorithms, it's important that they are reliable, meaning you can check that they are working and doing what they are supposed to do, which is particularly important because quantum systems are noisy. In the theory of classical computation, usually we check more easily solutions to problems, like there are this class called MP. I think checking that the quantum computer is working without error correction is difficult. Also, we typically want practical applications. I don't know, but I think most people here are academics. Who is not an academic here who is working in industry? Okay, yeah. So practical for academics is close to what I'm going to talk about. But when people talk about practical in companies, they want you to have a business canvas for a company that will last at least 5 years or something like that, and you can hedge investors and hopefully survive doing at least some product. Like, D-Wave doesn't have a credible quantum speed and claim, but they are doing something sufficiently practical to last decades. So that's practical for in industry, but here practical is between something that has some quantum advantage to something that has quantum advantage for something that people care. When people care, when we talk about people caring, we always have to define relative to a community, okay? So there is practical for condensed matter physicists, there is practical for companies, there is practical for many people, and then there is practical for Juani, and practical for Juani is almost everything. So, because I'm a theorist. But anyway, now, why do you care so much about this problem, or I care about this problem? Imagine you have a quantum computer. Imagine you have an application and you tell me, wow, you found an algorithm, it's cool, amazing, let's go play with the computer and solve some problems. Now, it's often happened in the history of quantum computing that people found candidates for candidate algorithms for very good problems with practical applications like Netflix applications or applications for industry. And then people found better classical algorithms that outperform the quantum ones. And that's kind of like, you get sad. But it's what it's what it is. Like, it has happened, for instance, in the context of quantum machine learning algorithms, there was a lot of motivation to look into it because people like Kerinidis and collaborators found algorithms for recommendation systems, like systems that recommend you content on the internet, in Netflix, in X, in Instagram. And they found quantum algorithms with exponential speedups for recommendation systems. And then here comes later, I find these headlines a bit adultist and disrespectful, but here comes major advanced teenager Wing Tang. At the time, it was this researcher working on her thesis, I think, and found better classical algorithms, or classical algorithms that were exponentially better, and then closing the gap of advantage for the quantum algorithms. Then the new classical algorithms discovered by Ewing did the same thing, collaborators, but they had they were exponentially better, and then the quantum speedup became polynomial. Also, D-Wave has claimed speedups lots of times, and typically they have been debunked or people have found alternative classical heuristics for doing similar things. There is no agreement on the fact that they have a quantum advantage. People in MIT in 2013, like I think Farley, Goldstone, I don't forgot the name of the third author. They found an algorithm based on the QAOA to solve an optimization problem called max K-SOR. It's like a variant of these optimization problems with constraint satisfactions, like 3-set. They found an exponential advantage for the best non-classical algorithm. That was a super cool result. Also motivated QAOA people to look into the QAOA. But some classical algorithm researchers got very interested in the result. After 10 years with no progress in this field, they found in a few months a better classical algorithm that also outperformed the quantum one. So yeah, these are examples where we dequantize quantum speedups after discovering them. You okay? Have a question? Okay, okay, now this is something more different, like a place where we do think we have quantum advantage is for problems like in simulation of quantum systems. We still do not know how to simulate them efficiently, like time evolutions of Hamiltonians. And in fact, in the field of quantum simulators, quantum simulation, the people already in 2012 and 16 were doing very large quantum simulation systems like Hall atoms in optical lattices. These papers over here implemented time evolutions of Fermi-Hubbard models, and these simulations were using lots of Hall atoms. It could not be efficiently simulated with the best classical algorithms available at the time, which were some variant of tensor networks algorithms, time DMRG. Now the thing here is people complain that you can actually reproduce some of the simulations doing some other calculations, like Boisho has a criticism. Sergei Boisho, although he only recovered the same calculation after the experiment was done, without predictability, so to say, but also there is the angry cat. The angry cat is a complexity theorist and doesn't like so much this advantage claim because there is no theoretical argument saying Win Tam is not going to come later and find a better classical algorithm. Some people then have looked into this problem more theoretically, like it's a classical simulation problem, designing examples of quantum experiments that we can run that with evidence, that theoretical evidence, strong theoretical evidence that they're not classically simulable. And people like Alonso and Arkhipov started looking into boson samplers, then Google on random quantum circuits. These are examples of programs, algorithms where you do random unitaries from some gate sets. Like here, these are linear optical unitaries using photonic systems, photons. You measure photons in the end with some constraints. I'm not gonna explain. Here we have superconducting qubits on a lattice, and then you do universal gates in different qubits in the lattice, nearest neighbor interactions. It's a 2D system, and then you make deep circuits here. Then you measure at the end, and you produce a number randomly, and the problem you are implementing here is a random number generator, which is designed by with this structure. So these circuits are generated in random quantum states. You measure them, and you get random bit strings. It's a peculiar problem called the sampling problem. We are not sampling a distribution that we want. We're sampling something random from the hard measure, so to say. These circuits, for instance, they approximate hard random unitaries. So pretty much what you're doing here is approximating the preparation of a random pure state. They are very entangled, and you sample from that. Now, these circuits are very hard to simulate. Classically, there is an intuition which you can see here. This is intuitive because of some reason. Imagine you have a theoretical method to simulate quantum circuits. Tensor networks exploit entanglement. Stabilizer formalism exploits stabilizerness. The covariance matrix formalism exploits something else. But when you do random sequences of gates, there is no structure in the circuit whatsoever. So intuitively, you cannot design an algorithm that will exploit a structure because there is no structure. These are very useful circuits you want to benchmark is a backend simulator. In your, you have a library and you want to see how much you can simulate. This is a good problem to simulate because they are hard to simulate the circuit with any method, and you can get numbers that you can compare between an architecture and another. So if I give a student a project on tensor networks and I give another student a problem on convex optimization, I make them simulate these things. I know that I can compare the numbers because it's not a structured algorithm. And also the other motivation is theoretical. People can prove with some theoretical complexity evidence that unless there is a collapse of complexity classes, this is not classically simulable. It's not a mathematically rigorous result. It has conditions, but it's an important feature. Then Google, some years ago already, before COVID, made a claim that they had demonstrated, realized one of these circuits, and they claimed it was a proof of quantum advantage or quantum supremacy. They said, I prefer to say quantum advantage. Now they realized one of these sampling circuits, and you can see this as an important technological benchmark because they passed a frontier of technology where we can already implement one of these circuits in a regime which is very hard to simulate. Also, for theory or computation people, it's a bit like a Bell test. Like when you want to do a fundamental proof that entanglement exists, you try to do a Bell test or something like a CHSH inequality. Here, if you want to do a very fundamental proof that you can make a program that we don't know how to classically simulate, this is what the best thing I could give. Because this is where I can trust that more the theory. The experiment had caveats, and it wasn't the first experiment of this, and it was the first experiment of this area, but as in many experiments, it's probably not going to be the last because it had flaws. One flaw that people from IBM pointed out is Google, in their paper, claimed that the cluster that they had could not classically simulate the sampler, but they assumed that the cluster could only use RAM memory. IBM had a paper, manuscript, checking that if you use the entire hard disk storage of the same cluster, then it was feasible to classically simulate. And then people debated, like, well, but it becomes way more expensive, and it gets more into a debate of numbers and how expensive it is, more than feasibility. There is also criticism from people that do verification, because it's hard to verify this device with noise. Now, these are details of the device. They did 50 deep circuits, depth 40, and the comparison was against 130,000 core per cluster. Okay. So now, as I said, we are building quantum computers in several places in Spain. This is part of the Quantum Spain initiative. My group is part of the initiative, and many of you are probably in groups that are in the initiative, and it's part of the Red Española de Supercomputación. And there are more resources here on quantum computing if you want to learn about it. I want to tell you now about high performance computing. What I'm doing now, I'm studying classical simulations and I'm building this cluster. And now imagine that you want to make quantum computers accessible, like as part of the network I just shown. Now you want to install the quantum computer somewhere. I'm going to come back to my question, are quantum and classical computers different? Who says they are different? Who says they're the same? Okay, now here is a thing. Where are you going to put a quantum computer in the university? You know you need a technician to take care of the computer, right? Where do you have a technician already in the classical cluster? What do people typically do is to put the quantum computer in the classical cluster. Now the quantum computer is part of the classical cluster, so is it different? Or you just have a classical cluster with a quantum accelerator or a quantum computer with a cluster accelerator? Because it seems to me that in the end you're going to put everything in the same place and it doesn't really matter what is better because you combine them. Now, that's my opinion. Now, in high performance computing, this is typically the situation. We have clusters with lots of units, we connect them. We have personnel hired in the cluster because these are complicated facilities. And typically there is a problem of how to solve a problem combining the resources available in the cluster. How do you use the most sustainable, efficient effort to use of resources And we have very different types of hardware in there already. Like we have, this is a CPU. This is a picture of a last generation CPU node. It's a Epic AMD CPU. I have 2 of these in my cluster. So you can see here, this has like 2. It's a supercomputer. These CPUs right now are very complicated. This is divided into 2 CPUs. There are like 48 and 48 cores in each. The RAM is here, and this is a bus. The speed of calculations in a cluster is so fast that every movement of a bit from one part of the chip to another matters. So actually, you have to move bits from this part of the RAM to here. This is not so good. And also, there are like local memories in here, cache memories, that allow you to move bits from the RAM to the fundamental processing units. These are called the L1 cache, the L2 cache, and the L3 cache. It's like a system of buckets. You wanna, you have a fire, and you have a piece of water. You make a change of buckets to get the bucket to the water. Those are the cache memories. Another type of device are GPUs, graphical processing units. These are being used for machine learning, data analysis. They are super powerful right now. They have a different structure. In the previous example, here typically we have many cores, but not as many cores as in a CPU and a GPU. The RAM is in CPU clusters is the largest available. RAM is, by the way, becoming super expensive right now. So RAM is we bought 2 nodes, and from the time where we bought the first to the time where we bought the second, the price has gone up a lot. The GPUs have more cores, but they are not typical CPU cores. They are different cores. The cores have different structure. They are tailored to do different type of operations, like these ones from NVIDIA are tailored to do a lot of things like tensor contractions. And the programs in here are independent. They don't communicate between themselves often. They are doing a job. When they finish the job, they communicate. They don't communicate usually while they are working. So it's a bit like having a bunch of professors solving a problem, that's a CPU, versus having the students of the university solving a problem together. The professors are very slow, but typically they can solve more complicated problems because they have more resources. But the communication between them can be sometimes complicated, and they are better for very demanding, highly specialized problems. But students can solve problems in parallel much better, more efficiently with less communication. That's a GPU. Or people a bunch of people in Reddit become pissed with someone who was rude to their favorite singer. And they go and trash the web page of the singer by doing service attacks to the web page. That's a good example of a GPU parallelization problem. Like everyone decides to attack the web page in parallel, and they do. That's like a GPU. Important thing, there are more cores. Programs are independent. The RAM is smaller, but still pretty large, and the communication bus is huge. There is a lot of communication between these. Cores is very fast. They're typically better for parallel problems. And now we also have field programmable gate arrays. This is like a quantum simulator. You have like a configurable device where you can configure something which are called LUTs. These are units where you can configure the operation that the chip does before you start computing. So there is like 3 steps in here. Before you start doing a computation in FPGA, you program the hardware to do a circuit. Then you load the data and the program, and then you execute a huge loop. And this is done so the hardware itself is configured to minimize the bit transfers. These things are way more complicated than GPUs or CPUs, but they are very good for energy efficiency. They can be they can improve the efficiency of calculations massively, which is a big problem now because GPUs are burning energy. So we are building a cluster like this, and also we are trying to get we have access to 2 quantum computers, and we're trying to get one. And you can see in the same cluster we have lots of units which are different. So what I'm doing now is using theoretical methods to combine all of these. I think we should have a small break and maybe have 20 minutes more, or. But I think we haven't done a break yet. I think I can make a break here. Yep. So if you want to go to the bathroom or have a 5-minute break, do so. I'm going to start. I'm going to change the topic of the talk now. We finish at 10, right?